Okay, when you're starting a problem that's asking you to calculate how much heat is required to heat a substance or how much heat is lost when you heat a substance from a certain temperature to another temperature, you're going to start with a set of equations that looks like this. You've got two equations. One is Q equals Cm delta T, and that delta is a little triangle. And then you have another equation that looks like this, Q equals M times delta H. Okay, so before I even start describing how to calculate this, I'm going to go over what these equations mean. So basically what these variables are that you're going to plug into these equations. And then I'll talk about how to solve the actual problem using them. So in the first equation, the Q equals Cm delta T, okay, you have a C, which stands for specific heat of the substance, and you can find the specific heat of substances in a chart, either in a chem textbook if you have one, or you can Google a specific heat chart, and it'll give you a list of different substances, the different states that they could be in, and the values for this. Okay, M in this equation stands for mass, which should be measured in grams. If the mass that you're going to use is not given to you in grams or it's not measured in grams, then you need to convert it to grams before using this equation. Okay, delta T stands for the change in temperature. And this variable is actually an equation within the equation. So delta T has its own equation, and that is the final temperature minus the initial temperature. And I'll explain that a little further when I actually calculate this out. Okay, for the other equation, the Q equals M times delta H, okay, M in this equation is for moles. So what you're going to do is you're going to take the mass that you used for the other equation and you're going to convert it to moles using the molar mass of the substance that the problem is referring to. The delta H stands for molar enthalpy, and this would also be found in a chart either in your chemistry textbook or you can Google molar enthalpy charts. There's two charts. There's molar enthalpy of fusion, which you would use in a phase change going from solid to liquid or liquid to solid. Okay, and then there's also one for vaporization, which you would use when you're going from a liquid to a gas or a gas to a liquid. Molar enthalpy in general is the amount of heat required to change a substance from one phase to the other, and then you have these specific charts dealing with the specific phase change that's happening in the problem that you're working with. Now what you're going to do is you're going to calculate a certain number of Q's based on the information given in the problem, and I'll walk through how to calculate that number of Q's in just a minute. But you're going to solve for a number of Q's. That number is either going to be just one Q if there's no phase change, or if there's one phase change there will be 3 Q's, or 2 phase changes there will be 5 Q's. But regardless of that, at the end of it, you're going to take all of the Q's that you calculated and you're going to add them up together to get your Q total. That's a TOT just for total there. So Q1 plus however many Q's you end up having. So what you're going to do to start solving this problem is you're going to read through the problem and pull out the numbers that are given to you because you're going to use them within these equations. So this problem says how much heat is required to heat 327 grams of solid aluminum. Okay, so there's a mass, and there's my substance right there, solid aluminum, from 305 Kelvin to liquid aluminum at 972 Kelvin. Okay, so there's our starting temperature, there's our ending temperature, and we are starting in solid and we're ending in liquid. Okay, and then it gives me a little after note here that says aluminum melts at 933.47 Kelvin. Okay, that is going to be important because it's a temperature that we're going to use for our delta T calculation. So the first thing I'm going to do to start solving this problem is determine how many Qs I'm going to need to calculate. So to do that, I'm going to look at the phase change or changes that are happening here in the problem. So in the problem, I underlined that we were starting with solid aluminum and ending up with liquid aluminum. So our phase change here is going from solid to liquid. And I'm going to assign a Q for each phase and a Q for each change. So I have a Q1 because I'm in the solid phase, a Q2 because there's a change, and then a Q3 for my liquid phase. The next thing I'm going to do is I'm going to pull those temperatures out that I underlined, and I'm going to line them up. Now, the way you're going to line them up is determined by what's happening to your substance. Okay, in this problem, it's asking how much heat is required, so you know that you are adding heat to the substance. So for adding heat, I'm going to start with my smallest temperature and line them up in order from least to greatest. If you're working a problem where it asks you how much heat is lost, that means you're removing heat from the substance, and in that case you would line your temperatures up from the greatest temperature to the least temperature. So for this problem, my temperatures are going to be my starting temperature, 327, oh sorry, that's my mass. Let me fix that really quick. Okay, so my starting temperature is 305 Kelvin. In order to make this phase change, I'm going to have to pass through the melting point so that the substance actually melts from a solid to a liquid. So 933.47 Kelvin, and then the problem tells me the temperature I want to end up with is 972 Kelvin. So the reason I'm lining up the temperatures is so that when I go to calculate my delta T, I'm not going to be able to make any mistakes here, because my temperature change for my first Q is going to be 305 to 933.47, so this is my initial and this is my final temperature for my Q1 calculation. Okay, my even numbered Qs, so my Q2, and if I were to have it, a Q4, would use the Q equals M times delta H equation, and in that equation there is no delta T, so I won't have a temperature change for any even numbered Qs. Then for my Q3, the 933.47 is going to be my initial temperature, and the 972 will be my final temperature for my Q3 calculation. So I've already set up my subtraction problems there. It's going to be this temperature minus this temperature for Q1, this temperature minus this temperature for Q3. So now I'm going to actually work the problem. So I have determined that I need 3 Qs, and I'm going to go ahead and set those up with the variables that I'm going to need to solve each Q. If I go ahead and set it up, hopefully that means I won't forget anything, and at the end I will come up with the right answer. So for Q1, it's an odd Q, so I need the equation Q equals Cm delta T. So I need a C, an M, and a delta T. And since in Q1 I'm in the solid phase, my C needs to be for solid aluminum. Sorry, that S didn't come out very well. Okay, for Q2 I need to use the equation Q equals M times delta H, because that is my even Q equation. So I'm going to notate that. And then my delta H, my molar enthalpy, will be molar enthalpy of fusion, because in this problem I'm going from solid to liquid. So I'll notate that really quick. And then for my Q3, another odd numbered Q, I still need C, M, and delta T. And this time my specific heat will be for liquid aluminum, because up here we notated the Q3 as being the liquid phase. Okay, so for my specific heat for Q1, I'm going to check my chart wherever it's available to me, whether it's in my textbook or whether I'm Googling the chart. But any way that I look this up, I'm going to find that the specific heat for solid aluminum is going to be 0.90 joules per gram Kelvin. Okay, and then while I'm looking at my specific heat chart, I'm going to go ahead and pull the specific heat for my liquid phase for Q3, which for aluminum, liquid aluminum will be 1.09 joules per gram Kelvin. Okay, and then my mass, if you remember, was given to me in the problem. It's something that I underlined. 327 grams of solid aluminum. So I'm going to come back down here and enter 327 grams for my Q1 and my Q3. Now I'm going to also enter it right here, but that's not going to be what I actually end up using to solve, because remember I said that the M in your Q2 equation, in your even Q's, needs to be converted into moles. So what I have to do is pull the molar mass of aluminum, which, if you look it up on the periodic table, is 26.98 grams per mole. And I'm going to calculate that conversion out, and what I should end up with is 12.12 moles of aluminum, and that's what I'll actually use for my Q2 calculation. Okay, and then while I'm looking at charts, I'm going to go ahead and look up my molar enthalpy of fusion for aluminum, which is 10.7 kilojoules per mole. And then I'm going to go ahead and calculate my delta T's. Now remember that we set up our delta T's right here. So I'm going to go ahead and make those calculations. For my delta T for Q1, I'm going to use 933.47 minus 305. And that will give me 628.47 for my Q1 delta T. And then for my Q3 delta T, I set that up here. That's going to be 972 minus 933.47, which is going to give me 38.53 for that delta T. Now that I have all of my pieces for each Q, I'm going to solve for each Q by multiplying its variables together. So I'm going to take my answers, my pieces for Q1, multiply those together. So that's going to be 0.90 times 327 times 628.47, and that is going to give me a total of 184,959, and my units on this problem, if I do the math right on the units, will be joules. For my Q2, I'm going to multiply my 12.12 moles times 10.7, and that's going to give me an answer of, of 129.68, and the units here should be kilojoules. And then for my Q3, I'm going to multiply 1.09 times 327 times 38.53, and that should give me an answer of 13,733, and just like my other odd Q, my units here should end up being joules. Now at the beginning of this video I said that once we had our individual Q answers, we would add them all together to get our final answer for the problem. But before we can do that, we have to make sure our Q's all have the same units. Right now I have joules for my odd Q's and kilojoules for my even Q's. So what I'm going to do is convert my joules to kilojoules, and I can do that really easily by just moving my decimal place 3 times to the left. So over here I end up with 184, sorry, I'm going to go ahead and round that, 185 kilojoules, and over here I end up with 13.7 kilojoules. And now I can add all of my Q's together, so that will be 185 kilojoules plus 129.68 kilojoules plus 13.7 kilojoules for a final answer of 328.7 kilojoules.